couple of, Eero and I occasionally just have our brains just go off in a zone where things just don't work. And so when I had this slide up a week and a half ago, I just had, I do the math ahead of actually writing it down in my head, and I kept doing it in my head wrong, so before I kept writing, I just got stuck. So let me get unstuck. So this, way back when, we were talking about the Gaussian and various ways to look at it, and one was just to write out what happens if you want to do a conditional, i.e., you have this two-dimensional Gaussian, but you want to know, if I know the second variable has a particular value, now what's the distribution for the first variable only? Okay? So that's just write out the Gaussian, which is actually not on this slide, but it's the, x minus mu multiplied through the covariance matrix, the inverse covariance matrix, which we call the precision matrix. So the inverse covariance matrix has elements like P11, P12, P21, P22, right? And so the math here is basically take the Gaussian and write it out, but put for x2, meaning the y-axis, x2, put in a particular value, okay? So that's now a constant, and see what you get, okay? So that's what we have up here, which is e to the minus 1/2, and now you've got, x minus mu multiplying through the precision matrix, which is a vector times a matrix times a vector. The x1 one will actually have an x1 in it. The x2 one will just be a constant. And so we're going to write not all the terms, because we don't really need to know them, because the thing you end up with is going to be a distribution in x1. So you get a lot of constant terms, but we don't really need to know them, as I will show you. Because what we have to end up with has to be a distribution, a density function. It has to be something that integrates to 1. It has to look like a Gaussian, as you'll see. So, the precision matrix, I have to make one of these. That was very, very useful. Okay, so, here's the Gaussian. It's got a constant out here. A constant out here. E to the minus 1/2 x minus mu. This one wants to transpose. Inverse covariance x minus mu. Okay, that's the Gaussian, where x is x1, x2. That's x. And mu is mu1, mu2. That's mu. This guy, we're going to give a name to. We're going to call it the precision matrix. P12, P21. These obviously are equal to each other because it's a covariance matrix. That's just all the terms in what you're looking at. Finally, this is going to get replaced with a constant in all of this. So then, if you just write all this out and see what all that vector times matrix times vector gives you, you're going to get the top one times the top one times the top one. So that's what this is right here. You're going to get some cross products where you get the top one times either of these times the bottom one over here, and vice versa. So you're going to get two of those. That's this. Two, where am I? Sorry, up here. That's two. P12 and P21 are the same as each other, so I'm only writing one of them. And it's a cross product of the top one, x1 minus mu1, and the bottom one. Finally, you're going to get a term that has to do with the bottom ones. That's just a constant, so I'm ignoring it for now. Okay? Now, so that's what you have up there. Now I'm going to do some algebra to just make it be a polynomial in x, x1. So there's only one x1 squared. It's right here, and it's times p11. So here's p11 x1 squared. Now we go look for the terms in x1. So again, these are all constants, so they're all irrelevant. This is an x1 minus mu1 squared, so you're going to get a 2x1 mu1 p11. So a 2 times x1 mu1 p11. By the way, I left out the minus sign, which would be just sitting right here. Okay? And then from this guy, you're also getting a 2p12 x1 a minus mu2. A 2p12 x1 times a minus mu2. Okay? So those are all the terms in x1 and an x1 squared. The rest are all constants, and we're going to just ignore them because we're going to fix them later. They're e to a constant, which means they're a constant. So that constant will come on the outside to make it add up to 1, and the other constant will set to be whatever we want. This is called completing the square. So before I continue, I keep waving my hand saying we can get away with this. So we've got e to the minus 1/2. That's what's written there, e to the minus 1/2. And now I'm going to be more general. Times ax squared plus bx plus c. That's what we have. Now, I've ignored c. There's a bunch of constants, but there's a constant there. I shouldn't use c because c is a covariance matrix. I'll call it d. Okay? That's what we have. And in general, one can play a game where you say, oh, I've got, let's take this bit. I can rewrite that as a times, let's make this b minus because it's always going to be minus when you're doing Gaussians. Okay? So I can rewrite that by saying, okay, I got a, so that's going to be x squared minus b over a plus d over a. Just a minor rewrite. And then I just can say, oh, sorry, times x. And then I can say, well, x squared minus something times x looks like the beginning of x minus something squared. So in other words, this can be rewritten as a times x minus, I'm going to make up a new constant, e squared plus f. Why can I do that? Because I can just figure out what's the constant I need over here such that it looks like x minus that squared, and then add and subtract it, and then absorb it into the other guy. Okay? Having done that, this is an exponential, so now I have e to the minus 1/2, this stuff, a x minus e squared plus f, and that's going to be the same as e to the minus 1/2 f times e to the ax minus e squared.
Minus 1/2.
Yeah, put my minus 1/2 here. Point is, this is a Gaussian. It's exactly in the form of a Gaussian. This is the mean. This is 1 over the variance. And this, I don't know what it is, but if I'm going to make it a density, I'm going to put the right constant here, which is 1 over square root of 2 pi sigma. So it's going to have to be that. I don't have to worry about it. So we can do the same game over here. So starting here, we have that. However, there's a way to skip all this algebra. And in some case, certainly in this 1D case, skipping all this algebra will be way more pleasant. And the way you skip all the algebra is, you know what the answer has to look like. Because you want to end up with e to the minus 1/2. Now I'm going to use the actual terms over there. X1 minus mu squared, over sigma squared. That's what you want to end up with. In other words, when we take this slice, we're going to have a Gaussian, it's going to have a mean, it's going to have a variance. Okay? Now that is e to the minus 1/2. Let's just write it out. X1 squared over sigma squared is going to be the x1 squared term. And then, oh, actually, yeah, that's fine. Minus 2 mu x1 over sigma squared plus a constant. I'm ignoring the constant because I won't need it. Okay? Which means, if I have a polynomial e to the minus 1/2 x1 squared times a constant, that constant is 1 over sigma squared. Right over here, we have e to the minus 1/2, there's the x1 squared, it's times p11. Which means we immediately know that p11 equals 1 over sigma squared, because that's what x1 squared gets multiplied by, which means we know that sigma squared
is 1 over P11. Okay. And we're halfway there already. We also know e to the minus 1/2 x1, the next term is 2 mu over sigma squared. It's negative 2 mu over sigma squared. So we know that negative 2 mu over sigma squared is whatever x1's multiplied by in these parentheses, which is this big long thing. Am I doing this right? Where did I write it? Here, just so I make sure I don't trip. Yeah. Okay, so there's a plus, this one's written as +2. That one's written as -2, which means I need the negative of this right here. So that is P11 mu1, 11 mu1, minus P12, oh sorry, first of all, -2. It's just the whole thing, except it's negative. So, I don't want to just start this. P1 minus, I started in the wrong place. P1 2a minus P2. P2a minus P2. Okay? Now, we already know that 1 over sigma squared is P11. We also know this is minus mu times P11. Okay? So the thing we don't, what have I done that's funny here? That's all right. Oh God. Here we go again. Should have started this 3 minutes ago, so I didn't do this so slowly. We want to solve for this new mu, i.e., what's the middle here? Well, where is it? It's right here. So all I need to do is divide out by P11. And when I divide out by P11, you get exactly this. Here's the mu1. First of all, the 2 goes away. There's a 2 on both sides. Sorry, I left the 2 out here. The 2's cancel. The minus P11 goes here. And so that cancels, and so you get that mu1, which is right here. And the last term, you get P11 over P12 times a minus mu2. Okay? So it's just the algebra of, I know the multiplier on x1 has to be this. So just set it equal to that and see what you get. So sorry I tripped on that last time, but all of this is just basically completing the square. It's saying, I got a polynomial second degree in x. That, by definition, is a Gaussian. So write it as if it is a Gaussian and compare the terms. And you compare the quadratic term, and that gives you sigma squared. And you compare the first order term, and that gives you mu. Okay? That's what I wanted to correct. You are gone. I'll fix this mess.
Catholics in the room? I grew up Catholic, so I have to say some Hail Marys or something to make up for the essay. And I have to make up for my failure to explain the bias in that estimator, or I can make up for my dancing. Mike and I both have to do penance for our dancing. For those of you in CMS, we had a big dance party on Saturday. Retreat tonight. Okay. Let's see. We did that. I fixed these slides a little bit, so what we'll put online will be, the notation's a little bit fixed, but we went through, nothing changed conceptually, it's just fixed a little bit more consistent notation. So we went through how do you do the MLE for the binomial. That was this. We did it for the Poisson. The idea is I'm going to measure a bunch of counts, or event counts, from some process that has a rate of generating events, lambda, a mean rate. But on each measurement, I'm going to get a different number, a different count. The k's are integers in this case. The lambda is continuous. It lies between 0 and something. And in the MLE for this case, if you take the log of this thing and you optimize it over lambda, you get actually the mean, the sample average. Okay? So here also, this is basically the average number of heads. It's the number of heads divided by the total number of coin flips, basically. So this MLE turns out to be basically the sample average. This MLE turns out to be the sample average. So you start wondering, and let me go to the Gaussian case, that's the next slide. Oh gee, now here's another MLE. Now we're trying to estimate two parameters, not one. There's a mu and there's a sigma. Think of the theta parameter vector as being a two-dimensional vector, not just one number that we're trying to estimate, but two. So here we have a bunch of data, xn, those are the measurements. We're trying to estimate mu and sigma. It turns out that when you calculate the MLE here, you again get the sample average. And in fact, the MLE for the variance is the sample average of the squared deviations from the sample mean. It's kind of makes sense. It's like the obvious and natural thing to do. But it turns out, and I've started to show you this last time and messed it up, this thing is biased. Okay, so why is it biased? This time maybe we can get it right. So just write down what it is. It's a sum of the xn's minus the mu hat. I'll just leave it as mu hat for now. And we have a 1 over n out in front, right? And we write this thing squared, okay? So this is our sigma hat squared. Right, I'm just copying what's on the slide. And now we write this out. I started to do this last time and I got, and because I wrote it with the expectation around it, I got myself tangled up because I thought, oh my God, now I have to work through all the cross terms and it's going to be a mess. In fact, you don't if you do the simple thing first. I just didn't recognize it at the time that I was writing it. Okay, so here's the simple thing. Do exactly what I started to write last time. I'm going to expand this as xn minus the true mu. And then we can do minus, let's say, the, let's write mu hat minus the true mu. Okay? So there's a distinction between the mu with the hat over it and the mu without. The one without is the real mean, and the mu hat is our estimate, which is written on the slide there. It's just the sample mean, okay? So now we write this, and we have 1 over n, and we're going to split it, we're going to multiply out. Now I have a difference of two things, and I'm squaring it, so I'm going to actually write this all out. I'm going to square this one, then I'm going to take minus 2 times the product of these, and then I'm going to square this one, and I'm going to separate them out, okay? So the first one squared, that's just xn minus mu squared. I still have 1 over n times the sum in front of it. Now I have minus 2 over n times the sum of the product. So that'll be xn minus mu times mu hat minus mu. Keep my hats in the right place. And then I'm going to have one more, which is the mu hat minus mu. And that's going to be squared. Oop, and I need a 1 over n in front of that too.
Well, start treating constants like constants.
Yeah, I will, but I'm trying to take it one step at a time. That's what's going to happen. So now I have, again, a 1 over n, and I have a sum. I just wanted to actually write it out so that you get something out of it, all right? So now, let's look at each of these terms independently. What's the first one? And in fact, what we're going to do, maybe we'll do this simultaneously. What I'm going to do is I'm going to look at each of these terms and I'm going to take its expected value. Because in the end, what I want to do is I'm trying to figure out whether this is biased. So what I want to know is the expected value of this thing. This thing is a function of the data, right? I take the data, the xn's. I first compute mu hat. That's on the slide there. And then I subtract it off of each of the data points, and I add them up and I divide by n. So this thing's a function of the data, and the data are randomly drawn from some distribution. So this thing is a sum of random variables, and so I can take its expectation. I can say, what's the average value of this thing if I were, let's say, to gather infinite amount of data? Or I can just say probabilistically, what's the expected value since I know what the distribution is. Okay, so I want to compute the expected value of this. And to do that, I'll take the expected value of a sum of terms is just the sum of the expected values. So I'm just going to take the expected value of each of these things as we go through. There are 3 things here. So this one is 1 over n times the sum of these things squared. So let's just, I'm taking the expected value of this, but you know, the expected value is a linear thing, so 1 over n, I can put it past the 1 over n, I can put it past the sum, and I can just take the expected value of this thing inside here. What is the expected value of a data point minus the true mean squared? I have a measurement x. I subtract off the true mean, and I square that, and I take the expected value of that. What is that? That's the true variance, right? So this thing is the true variance, an actual sigma squared. Not my estimate, it's the real thing. Okay, and now I sum this over the n data points. Well, it's sigma squared for every one of them. It's not different for each data point, it's the same. The expected value is the same. So if I sum this, I'm going to get n of them, n copies of sigma squared, but then I divide by n, so the whole darn term is just sigma squared. Okay, so this whole term, this thing is sigma squared, I'm taking n of them and I'm dividing by n, so I get sigma squared for the whole term. Okay? So that term, sigma squared. Next term. Well, this is a sum. The sum is over the little n, right? So this thing is just a constant as far as this sum is concerned, right? So I can pull this out and say this is just a sum over the little n's minus mu, right? And the sum, well, actually we can kind of see where this is going to go. When I go to, let's pull that out. Let's write this as, let's write this one as, I'll write 2. I've got an n here, and I've got I'm going to pull the mu hat minus mu out of the sum because there's no little n in it. I'm not summing over this. This is just a constant as far as this sum is concerned. And now I have still the sum over little n. I haven't been writing the little n here, but I'm writing it more explicitly now just to make sure that we're clear about why I was able to do this. And now I have a sum over these guys. And that's just a sum over a difference of things. And what's that going to be? Well, the sum over the xn's is just, if I divide it by n, that's mu hat. Here's a divide by n out here. Let's put that divide by n in here. Let's leave the 2 out in front. Let's put the divide by n like this. Okay. So the sum over the xn's divided by n, that's mu hat. The sum over the mu's, well, they're all the same, so it's going to add up n of them and then divide by n, so that's just mu. So this whole thing is 2. I still have this mu hat minus mu out in front. And this thing becomes what? Well, this thing will become mu hat because I've got the sum of the xn's divided by n. And this thing will become the sum of the mu's, that's n mu's, divided by n, so that's just mu. Oh, that's kind of nice. It's mu hat minus mu, this thing. And it's multiplied by mu hat minus mu. So the whole thing becomes, there's a minus sign here, minus 2 mu hat times minus mu times mu hat minus mu. Or if you like, mu hat minus mu squared. I'm doing it in place. Okay? So this is a minus 2 mu hat mu squared, this whole term, and one more term. This one is mu hat minus mu. There's no n's in here. This is a sum over little n, but there's no little n's in here, so basically I'm just going to add up n copies of this, and then I'm going to divide by n, so it's just that thing, i.e. this one is just mu hat minus mu squared. Oh, nice. So this is mu hat minus mu squared, but there are two of them and it's negative. This is mu hat minus mu squared, and there's one of them and it's positive. When I combine those, all together, I have sigma squared minus, it's minus 2 plus 1, so I have minus 1 of these guys, mu hat minus mu squared. Oh, and I didn't take the expected value, so that's the last step. I took an expected value of this thing. What is the expected value of this thing? What is this? What is this? I have to take its expected value, right? Because there's still, this mu hat is still a function of my measurements. It's a random variable. What is the expected value of this thing? Mu hat itself is my estimate of the mean. It's the sample mean, right? And this is the sample mean minus the true mean squared. And now I'm going to take the expected value of that. What is that? Well, when we have samples, we take the mean, and we say that's our estimate of the mean. And then we have some way of calculating how good is that estimate, right? We take we compute the standard error of the mean, right? We take the sample, we take the variance of the real thing, and we divide it by n, and that's the standard error of the mean, right? So this is just the SEM. And in fact, you know what it is. It's not sigma squared, it's sigma squared divided by n. The expected value of this thing, it's mu hat minus mu quantity squared. The expected value of that is the standard error of the mean. It's the thing that it's the variance of the x's, but it goes down. The more x's you gather, the smaller this gets, right? And it goes down as 1 over n, and it's like this. It's sigma squared. It's the variance of the x's, but divided by n, because every time you make another measurement, you get more accurate, right? So that's what this is. It's sigma squared over n. So now we see what we wanted, which is that this estimate of the variance, the one that's on the slide, and the one that is the maximum likelihood estimator, is not in expectation. It's not actually equal to the true variance. It's a little less than the true variance. It is biased. And this is of course in expectation, that is on average. Okay? So what I didn't write here is that I'm computing the expectation here. So when I first wrote this out, I just wrote this out with all the sums, but let me just write it on the side. I'm going to take the expectation, I'll just write E with this funny looking E. I'm going to take the expectation of it in these guys, with just writing out the sum up top, and I took the expectation. When I took the expectation, I got this sigma squared minus this little offset. So what you can see is that this thing, on average, is not equal to the true variance. It's equal to the true variance minus the true variance over n. Or if you prefer, it's the true variance times 1 minus 1 over n. Right? We can factor out the sigma squared. I'm not going to write that because it doesn't matter. The point is, this thing is not equal to the true variance, but the more data I have, the closer it gets, right? Because if I gather more data, n is going up, more and more data points. And asymptotically, in the limit, as I gather lots and lots of data, this term's going to get really tiny, right? I'm going to divide by a million, right? I make 1 million measurements. This is sigma squared divided by 1 million. So basically, this thing is equal to sigma squared, because it's sigma squared minus 1 millionth of sigma squared. So it's basically sigma squared. So this thing converges asymptotically to something that's unbiased. That's what we mean when we say that MLE is asymptotically unbiased. I told you that last time. Asymptotically, in the limit of infinite data, it's unbiased. But with finite data, if I only have 5 data points, then actually this thing will give me an estimate which is, on average, 20% lower than it should be, right? This is going to be the sigma squared minus 1/5 of sigma squared if I have 5 data points. So I'm going to be 20% below where I should be. So it's actually pretty significant if you have a small amount of data, but if you have lots of data, you basically don't worry about it. Okay? So, and you probably all know that when we estimate variance, there's a correction. It's kind of obvious. Now I'll write it. So this is sigma squared of 1 minus 1 over n, or if you prefer, you can write n minus 1 over n. It's the same thing. Just do 2 little manipulations. It's just algebra. N minus 1 over n times sigma squared. How can I correct this? The fact that this is always off by some fixed proportion, this is not dependent on the data. This is a number that depends on how many data points I have, but it doesn't depend on what measurements I made. There's no x's in here. This is just about the number of data measurements. I can fix this estimate, and it's easy to see how. Take this estimate and multiply it by n over n minus 1, and then you will correct it and make it unbiased, right? Even in small numbers of samples, it will be unbiased. So what does that mean? It means go back to the beginning. Here I have 1 over n times this, multiply it by n over n minus 1, and what happens? The n's cancel, and you get 1 over n minus 1. And you've probably all seen that, right? People tell you when you want to compute an unbiased estimate of the variance, what you do is you add up, you take all your data, you subtract off the sample mean, you square the differences, you add them up, and instead of dividing by n, which would be kind of the normal thing to do, the most obvious thing to do, you divide by n minus 1. And that seems kind of weird. Why would I divide by n minus 1? And the answer is this. The answer is you are correcting this factor so that your estimate will, you're basically slightly boosting, you're taking this sample, this average of the squared differences away from the sample mean, and you're boosting it a little bit, right? You're not just leaving it like this, you're going to boost it a little. You're going to multiply it by n over n minus 1, which is a number that's bigger than 1, right? Boost it a little. Okay, so that's what I started to write last time and messed up. Okay. And hopefully this helps at least a bit to see where it comes from. Right. You're not going to be asked to derive this, but I think it's good to have a sense of where these things come from. It's not like something somebody made up, right? It actually comes from a very logical process of thinking through what is the estimator, write down the MLE, is it biased? This one is not biased. This one is biased, but can be corrected. Biases cannot always be corrected. This bias can be corrected. Why? Because it's a simple scale factor which does not depend on the data, and it's a fixed scale factor and something that you know. So you can undo it by just multiplying by the inverse of this scale factor, and you can fix it. A lot of times when you have biased estimates, you can't fix them because the bias is some complicated function that depends on the data. And you can't actually solve for, you can't back your way out of getting rid of the bias. So there are many cases where estimators are biased and you can't just correct it. But in this case, the correction is a very easy one. And this is a very standard thing. And in many textbooks, you see people say, compute they don't call it the sample variance, they would call it what would they call it, Mike? What's the word that people use when they use the n minus 1? Is there a word?
Sample variance.
But that's not, well, I don't know. I think of this as the sample variance. We're having a word, a nomenclature problem.
You're just
because I'm weird, I know.
dyed in the wool baby.
Okay. Well, in any case, it doesn't.
The main difference is that they call it s squared instead of sigma hat squared.
I see.
And they call it x bar instead of mu hat. But they call those the sample mean and the sample variance.
The point is that whenever you compute any of these things, you are computing an estimate of something, and you should be aware of that. You're not just plugging something in, you're computing an estimate, and you should be thinking about what properties does that estimate have, why am I using that estimate? And you don't have to think about it that hard for these simple cases. These things are so standard and so widely used that everybody just does it. It's sort of automatic. But when you get into more complicated situations, when you're fitting a parameter of a model, then you have to think more carefully about what your estimate is going to be and how you're going to compute it. We're going to get sort of the edges of that in this course. We're not going to do really complicated examples, but we'll do some that start to look a little more complicated so you can start to get a flavor of what that looks like. Okay, one more example. Because I wanted to do another example where it didn't come out to just be the sample average. Because you go through those previous 3 examples, and it looks like every time you want to estimate one of these parameters, you just take the sample average. If you want to estimate the mean anyway. And that is true for all 3 of the examples I just showed you, but not for this one. Okay, so now I have samples from a uniform distribution. So those are the x's. I'm trying to stick to the same notation here. So the x's are the measurements. I have a bunch of measurements that are x's. The theta here is going to be just to keep it simple, we'll imagine that this is an interval that starts at 0 and goes up to theta. That's the maximum of the interval. And so let me just draw it. I should have a picture of the slide. So the probability looks like this. Here's 0. And it's uniform, it's constant out to value theta. Theta's positive. So this is constant out to theta. And of course, since it has to integrate to 1, the height has to be 1 over theta, right? Of course, because this is a rectangular box. So its area, if you like, is theta times the height. The height better be 1 over theta if you want the area to be 1. Okay? So this thing integrates to 1. And this is p of x given theta. Now I'm going to observe a bunch of x's. Well, you can start with just 1x. If I observe 1x, it's drawn from here, so it can be anywhere in that interval. And I want to know, well, what's the maximum likelihood estimate of theta? Theta's the outside end of the interval, right? How do I choose that? Well, I just write it down. So p of x given theta equals what? If I have only 1x, what's the probability of x given theta? I think it's on the slide, more or less. Still nobody's going to tell me. It's 1 over theta, i.e. it's the height of that box, that's the probability, if x lies in the correct interval. If it's outside of that interval, then the probability is 0. Right? We might as well specify that. All right. So that's pretty easy. Now I want to know, I do this bizarre thing that we do with maximum likelihood estimation. I take this probability density, which we usually think of as, well, here's a fixed parameter, and here's the random variable x that is drawn as a sample from this distribution. But now I'm going to flip it around and do something a little weird. I'm going to imagine the x are data measurements. Let's start with just 1. I make a measurement of x. It's somewhere in this interval, whatever. Let's say I measure x and it's here. And now I'm going to hold x fixed to be the actual measurement that I just made. And I'm going to flip this around in my head, and I'm going to ask, what is the theta that maximizes the probability of having observed that x? It's a weird thing to do. I already mentioned this, but I'm saying it again because it really is kind of weird. You are treating this probability, which was originally envisioned as something where theta was a fixed value and x is a random variable, you were treating it the other way around. X is now the fixed value, that's the measurement. And theta is the thing you're trying to mess around with, adjust, in order to maximize this thing. Okay, so how do I pick the theta that maximizes this thing? Well, it's pretty easy. What is the value of this thing as a function of theta? So let's write the likelihood. This is p of x of theta, but I'm going to let me write L of theta to represent likelihood. L of theta is the likelihood, which is just equal to p of x given theta, where x is my fixed data observation, right? So let's say that x is here. If this is true, if the x is less than theta, that means what's the value? The value of this thing is 1 over theta, right? So as a function of theta, the x has to be less than theta, so I better have theta to the right of here only. And what is the value of the likelihood? Well, it's 1 over theta. So if I plot this, or I plot the function 1 over theta, it looks like that. That's 1 over theta, right? Something that falls as the inverse of theta. As theta gets large, this thing gets small. Eventually it goes asymptotically to 0, right? And what happens here? Well, when theta gets down to x, that's as small as theta is allowed to be, right? If theta was smaller than x, I would have a problem, because I would have just observed an impossible data point. I observed this x. This is the x I just measured. theta's not allowed to be smaller than that because I just made that measurement. That means that theta has to be at least that big. It can't be smaller than that. If it was smaller than that, then this couldn't have happened, right? If theta was smaller than x, then the probability of that event actually happening would be 0. Could not have happened. So I cannot, this is off limits right here. I put a big X in it. You're not allowed to, X is not a data point. X is, do not go here. Where's the red marker? Warning, warning, do not go here. Okay? You're not allowed in there. You're only allowed out here. So here are your thetas. Here are the allowable thetas, and here's the value of the likelihood for those thetas. It kind of starts here and it falls as 1 over theta. Okay, so now, what's the question we're asking? Where's the theta that maximizes the likelihood of my observed data point?
Well,
I don't know. Where's the highest value of this curve? You're not allowed over here. Basically, think of this as 0. This doesn't happen. So where's the maximum? It's kind of obvious, right? That's the highest point. Everything else gets lower because as soon as theta gets larger, it's going to keep going down, 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 down. It's not ever going to go back up. So this is it. This is the best you can do. So what's the answer to the question? What's the maximum likelihood estimate? In this case, it's just pick theta hat equals x by measurement. Okay. What if I made 2 measurements? What if I made 100 measurements? They're all independent. So I make n measurements. Okay? What's the likelihood? Well, it's now the likelihood. Let's write L of theta. I guess what we'll do is we'll write. I don't like introducing more notation for this. It doesn't really help. So let's just do it this way. What's the probability of observing a set of x's? There are going to be n of them, which is consistent with everything we've been doing. And they're drawn independently. So what I can write is that because they're independent, the probabilities, the overall probability of observing all these x's is just the product of all of their probabilities, their individual probabilities. So it's just the product over little n of p of xn given theta. And each one of those, what's the probability of each one of those as a function of theta? It's just 1 over theta. And there are n of them, and they're multiplied. So the whole thing is 1 over theta, now raised to the nth power. Right? Okay. So now we go back to the picture. Here's the picture. Here's theta. Here, I observe a bunch of x's. Here are my x's, x1, here's x2, here's x3, here's x4, here's x5, whatever order they come out in, it doesn't matter. Here's a bunch of x's that I observe. And now what's my likelihood? Well, same thing I said before, theta has to be bigger than all of these. If theta were less than any of them, it wouldn't make any sense. It's an impossible thing, right? Because if you can't observe an x that's larger than theta. It's not allowed. That's what this means. Okay? So that means that, and if theta is bigger than all of the x's, then it's equal to, then the likelihood is 1 over theta to the n. So if I write likelihood here, right? This is likelihood. I'm going to plot it against theta. Now it looks kind of like the previous one, but it falls really fast. Now it's falling as 1 over theta to the n, so it's like, sorry, that's a capital N. Total number of data points, it's not a little n, it's a capital N. I'm imagining this is from n equals 1 up to capital N, right? I have capital N measurements. We're sticking to that notation. Little n is the index, capital N is the number. We did that when we did linear algebra too, right? Vectors. So same notation. Capital N is the total number of measurements. So this thing falls as 1 over theta to the n. And once again, once you get down back to this point, which point is this? Well, this is the first one you encounter as you're working your way back. It's the largest of the x's. I don't know which one it is. It could have been the first sample, it could have been the last sample, it could have been something in the middle. It doesn't matter. Whatever the largest one is, at that point, you've got to stop. You're not allowed to make theta less than any of these x's, including the last one. So none of the x's can be greater than theta. that's off limits, not allowed. So once again, I get to rule out this whole area, and I get to say, where's the maximum of the likelihood? And the answer is, once again, just like last time, it's here. And now that corresponds not to any particular x. And we only had one x, that was just equal to that value of x. Now what is it? The last x that I observed? No, it's the maximum. I take the whole set of x's that I've got, take the biggest one, that's my estimate. Okay, so at least now we got to an MLE that is not just taking the average. This is pretty far away from taking the average. You don't take the average of all these data points. You take the maximum. You take the largest one. That's your estimate. And it turns out, but I think to save time, since we're off to a sort of slow start, I'm not going to prove this to you. It turns out, you can prove, it's not that hard, but it takes a little bit of notation and time, that thing is biased. So now we have an estimate of the primary parameter. It is not a sample average. It is a sample maximum. And it is biased. You can kind of see that, right? How could it possibly be right if I only have a few points measured out of the interval? What are the chances that the maximum one is going to be actually the maximum of the range that I could have drawn from? I mean, usually you're going to draw stuff that's kind of scattered around, but the largest one will not be out near the maximum. Now, of course, once again, asymptotically, as I gather more and more and more and more data, eventually I'm going to gather a data point that's way out right near the edge, near the maximum. And then it will become unbiased as I gather that huge amount of data, as I go toward infinity. But for any finite sample, if I only have like 2 samples, or even 1, this is pretty biased. What do you think happens? What do you think the expected value? Actually, it's pretty easy. Let's do the 1 sample case, and then you can see it, right? I draw 1 sample out of the uniform distribution. And we already said my maximum likelihood estimator is just to take that sample as the maximum of the range, right? Just set theta hat equal to that x, the one that I just observed. What's the expected value of that? What's just the expected value of one measurement? And what's the expected value of one measurement when this is my distribution? Where's the mean of that distribution? Any guesses? Where's the mean of that distribution? Please, somebody tell me. It's not hard. Where's the mean? Oh my God. Sit down.
It's a seesaw. It's a seesaw. Where do you balance that rectangle?
Where's the mean of that distribution? Right. It's just in the middle. It's theta over 2. That's the mean. So, on average, if I draw a sample out of this thing, where's it going to be? On average, if I did it an infinite number of times and I averaged all those cases together, I would be right here, right in the middle, on average. Half the time I'm going to be larger than that, half the time I'm going to be smaller than that, but on average it's going to come out here. So that means that on average, if I use this as my estimate of theta, it's really biased. The actual value that I'm going to get is theta over 2 on average. I'm supposed to be estimating theta. So that's a pretty lousy estimate. It's way off. Now if I have 2 samples, it's going to be a little better. And if I have 3 samples, it'll be a little better. And if I have 1,000 samples, well now, if I have 1,000 samples out of here and they're distributed like this, there's probably going to be one of them that's out here not too far from theta. So I'll start to get a pretty decent estimate. And if I have 1,000,000 samples, then I'm going to get something very close to theta. If I have 1 billion, right? As the number goes up, I'm going to pack this interval full of sample examples that I'm going to draw. And there's always, the maximum is going to keep creeping up, closer and closer to theta. And in fact, so this is a biased estimator. It turns out, once again, this is a bias that can be corrected. And you can do a trick just like we did with the variance, the sample variance before, to correct the bias. There's another way to do the estimate instead of just taking the max. So you can either take the maximum and correct it, but there's another estimate. It's not the MLE. Can anybody imagine or think of an estimate that might work pretty well? This used to be a homework problem, but I think we took it off. What's a good, what could you dream up, given what I just told you about the mean? Maximum plus minimum, okay. So you could take the maximum, maybe the average of the maximum and the minimum. And, right? Take the max, got a bunch of samples, take the largest, take the smallest, average them together, and that gives you something that's in the middle. Oh, but you're right. Instead of that, you want to double it. But if you do that, so good idea. So you add together the max and the minimum. Now, why just use the endpoints, the maximum and the minimum? Why not use all the data? You have all these other things that are based on sample means. What happens if you take the sample, let's call it the sample average. Let's take the sample average. What do we expect that to look like? Well, that's going to be pretty close to the true average, which is the theta over 2. So we have a good way of estimating not theta, but theta over 2. So you could take the sample average of all your data, just average it together the way we always did. We all agree that's a lousy estimate of theta, but it's actually a pretty good estimate of theta over 2. So just take the sample average and double it. Or if you're working on a more general case of a uniform distribution that goes between, let's say, A and B instead of 0 and theta, well, you could just still do this. You take the sample average, and then you have to subtract and add from that, I guess, the maximum and minimum. Yeah, that's not going to help. Let's stick to this case. So this works pretty well, actually. And you can show that that estimator is, actually, I'm not completely confident about this, so I shouldn't say it. First, but it is unbiased. You take the sample average and you double it, that estimate is unbiased. And what I don't know, what you would like to know is, what is the variance of that estimate compared to the variance of taking the max, or taking the max and debiasing?
It's got to be better.
Mike says it's got to be better. You know what the variance of this estimator does, because it's a sample average. You know what that does. We just had it on the board. It goes as sigma squared over n, right? So it's got a variance that falls as 1 over n. So the question is, what does the max do? You take the variance of that. Does that fall faster or slower or about the same as this? And this is, I mean, I'm not going to work through this because I'm not really, I decided I wasn't going to write it all out, but this is a kind of exercise that you could imagine doing. You have two possible estimators. One of them feels like it should be the right thing because it came from the maximum likelihood concept, right? We derived this. I didn't write the actual estimator, but coming from this analysis, theta hat equals the max over the x-axis, right? You just pick the maximum over all the x's. And then there's a bias-corrected version of that. So you could go through the analysis, and you could do it either through simulations. You could actually draw samples from a uniform distribution, and you could compute these two estimators, and you could do this on different batches of samples, and you could estimate what is the variance, what is the mean, and what is the variance of these two things, and which one are they both unbiased? Can you make them unbiased? And once you've got them unbiased, what does the variance do as a function of the amount of data that you have? And you could make a decision about which estimator you like better, based on whether it's unbiased and what does its variance do as a function of data. Okay? And that would be a rational way to make a decision about which estimator to use, instead of just insisting on the maximum likelihood principle. I'm pretty sure Mike's intuition is right, which is that this estimator, the one where you take the sample average and double it, is actually better in the sense of variance and the convergence of the variance. Okay, I think that's all I'm going to say in terms of examples. I wanted to stick that one in because it's a bit different than the others. Okay? So you get to see, and this is still a pretty simple example. We could write it down, we could sort of figure out what it should be. The more complicated your model is, your probabilistic model, the more complicated it might become to write down a maximum likelihood estimator. And eventually, you can't write them down, you can't solve for them, you have to use a computer to optimize, right? So the maximum likelihood estimator is the solution to an optimization problem. By the way, just like regression. All the least squares regression we did is a solution to an optimization problem. That's how we introduced it and explained it, right? You say, what is the slope of the line that minimizes the squared error? And it turns out that linear algebra gives us a collection of tools to solve those problems explicitly and directly, so we don't have to like run some sort of an algorithm to solve for that problem. We can just write down what the calculation is in terms of linear algebra, and we get the solution directly. These things we're writing down directly. But in many real problems, you can't do that. You can't solve explicitly. What you have to do is plug it into a computer and say, please optimize this function. Here's the likelihood function. Here's the data that I just measured. Please optimize this. Find the theta that minimizes this function. And the computer will search, usually by measuring the gradient of the function, the derivative, and trying to go downhill until it gets to the bottom. It's going to look for the minimum or the maximum of the likelihood or the minimum of the negative log likelihood. Remember, we went through this whole thing about you can take a log, you can negate it, flips the maximum to the minimum, whatever. It's still an optimization problem. The computer is going to have to solve for the best point, and you will not be able to get that in closed form. And so then it opens up a whole new territory of things that you have to worry about. You have to worry about whether you can solve that optimization problem, whether the computer can actually get to the minimum. How long will it take to get to the minimum? So at the very least, you're introducing a lot more computation, and you may also be introducing a lot of conceptual difficulty because you're not going to be sure that you have the right answer. You might get stuck somewhere. And so that might not be the maximum minimum. It might be kind of a local minimum, and there's another one. Just over the hill, there's a better one. So I'm trying to give you a little bit of a sense of the landscape, that the closed form solutions, the things we did with least squares, where you can write down the answer, have a huge, huge benefit. It's just hugely beneficial to be able to solve correctly and directly for the answer and not have to go run some optimization procedure and cross your fingers and hope that it works. So, we still have to do that for hard problems, but you should always be trying to, first of all, try to solve the simpler problem first. At the very least, you'll then have it as a reference to compare to. So if that means linearizing things or assuming that distributions are Gaussian, that's often what we have to do as a starting point, because it allows us to actually get closed form direct expressions for the answer, and then we can feel sure about them and we have something to compare to and to reason against when we go to use a more complicated solution.
And intuition and 275 will get you uptown. Taking all your samples, divide and multiplying by, taking a sample mean and multiplying by 2 is not the right way to do it.
Really?
The right way to do it is take the max and correct it.
Really? Because it's a lower variance estimate?
It's a UM estimator. I just found
Really?
a paper that proves it.
It's surprising because usually things that depend on plucking out one data point, the max in this case,
Well, you're still
are
using
not as
all the data.
robust. You're using all the data, but not very strongly.
Yeah.
Right? You're not counting on much about the. You're not using
Unless I found a wrong proof.
No, it might be correct. We stated an intuitive guess, and we were wrong. It'd be good to see how much better.
The correction is to multiply by 1 plus 1 over n.
Does it strictly dominate it for all n? It's always better. That's hard to believe.
Well, it's the less than or equal to is what they call a uniformly minimum variance unbiased estimate.
Uniformly, that means for all n. All right. Homework.
Ooh, no. Maybe try it.
We won't make you prove it, but we might make you simulate it. Okay. These days, and that gets us to our next point. These days, computers have entered statistics in such a huge way that it's often the case that people don't work through closed form expressions or write down or try to calculate things about likelihoods. They just do simulations on a computer. Lyndon is going to tell me I have to stop. Is that what that's for?
Yes.
Okay. Take a break. Okay. Now we want to think, what I want to do is say a little bit about simulation and resampling. Okay. So This is our picture of the probability urn and the data. So over here is the urn. It has some model that we believe is what generates the data, P of x given theta. We get the data. That's a collection of xn's, samples that are drawn from the urn, usually assumed to be independently drawn from the urn. That's our x's. And all the examples we just went through are of this form, right? And then what we do is we write down a way of estimating theta given the x's. So an estimator, or estimate, is just some function of the x's. In general, it can be whatever function you want. You can make stuff up. You can just guess. You can say, oh, this seems like a good way to figure it out, and you can stick something in. And what we've been talking about is how do we evaluate whether this is a good estimate. Okay, and we have these two basic things that we ask that are very standard, that go back more than 100 years, which are you ask, is my estimate my theta hat? On average, if I were to repeat this experiment an infinite number of times, is the theta that I'm getting on average, the theta hat, on average equal to the true theta? That's whether it's biased. And then you might ask, okay, and also how variable is it? How much does it flop around? If I were to do this, run this experiment 10 times, each time grabbing the same amount of data, and I get 10 different estimates of theta, 10 different theta hats, are they close to the same value, or are they flopping all over the place? I want to know that because when I state what my estimate of theta is, I want to have something like a standard deviation associated with that, or maybe confidence interval. I want to say I think the true thing is in some range, 95% confidence interval. We talked about the fact that you can just express dispersion. This all goes back into expressing like central tendency and dispersion, right? I want to tell you what I think is the right value. I'd like it if that on average is correct. That's unbiased. And I want to tell you how sure I am about it, like how spread out it could be around that value, given that I don't know that that's exactly right. Okay, so how do we do that? Well, we went through, there's all these standard and classical ways of doing this. If you're measuring something that's a sample mean, then we know how to estimate confidence intervals, we know how to estimate the variance, that's the standard error of the mean, and et cetera. If it's not such a simple thing, we can take, let's say we're doing a maximum likelihood estimate, and the maximum likelihood estimate is not a sample average. Well, we can do, I mentioned briefly last time, and I've decided I'm not going to elaborate on it because it gets pretty complicated. But the basic idea is you can take the log likelihood function and you can expand it as a Taylor expansion into a second order term. And you can measure what the size of that second order term is, and that tells you basically how sharp your optimum is. And if you think about it probabilistically, since this is the log likelihood, or the negative log likelihood, what you're really doing by approximating with a quadratic function, a squared term, is you're kind of fitting the probability with a Gaussian. Because if I undo the negative in the log, it's e to the minus that squared thing, which is a Gaussian. So you're kind of fitting the likelihood as if it's Gaussian, locally Gaussian. And you're describing the width of that Gaussian. Okay, so that's another way to get a confidence interval. But these days, the most standard things to do are with just sort of two methods. One is just straight simulation. Okay, so I have this model P of x given theta. I get my data. I measure however many data points and data points. I get my estimate theta hat. Let's say I already know that my estimator is unbiased, and I want to know something about the variance, but I'm not sure what that is because this is a complicated function. What I could do is just do a simulation. So I can take the theta hat that I've got. I can plug it back in over here and know what this function is. And I can run on a computer. I can simulate drawing samples from this distribution, n samples, rerunning my estimate. And each of those are going to be fake. They're not coming from real data. They're coming from data drawn from this distribution. It's a little bit circular here, where I've already plugged in an estimate of what I think this theta is. But I'll at least get some estimate of how that flops around as I go through this process of drawing samples from that distribution and re-estimating. So I can estimate a new theta hat from each resample, simulated sample. And I can look, what does that distribution of theta hats look like? I have the true theta hat, the one that I got from the data, and then I have all these simulated ones that'll be around it. And I can ask, well, how spread out is that? And that will depend on how much data I have and how good my estimator is. And it'll give you some sense of how confident I should be in this. Okay? So that's sort of straight simulation. That's a fairly easy thing to do if you've got a model that you believe in and you can draw samples from it. And we talked about how you draw samples from probability distributions. the slides, if you look at the slides that are online, there's 2 slides that describe how to draw a sample from a probability distribution, and I greatly enhance those so that it's easier to read and understand what the process is, because we went through that kind of quickly. So that's online if you go and grab those slides and look at the 2 slides on sampling from a distribution. Okay? It involves going through the inverse cumulative, right? You take the distribution you want, you take its cumulative, now you draw a sample from the uniform distribution and you run it through the inverse of that cumulative function, and that gives you a sample from the desired distribution. I just said it in words, but it's all mapped out on those 2 slides. Okay, so we can do simulations, but there's another procedure. It's a very weird procedure, but it goes like this. Let's say I've got an estimate for something that I kind of believe in, but I don't really have a proper probabilistic model, or this is difficult to draw samples from, or whatever, or I don't really believe my model. I'm kind of, maybe I don't trust this model, this probability distribution, and I kind of want to just work with the data. And the idea now is that rather than resampling from this urn, which involved me producing this probability distribution and finding a way on a computer to just draw samples from it, I'm going to do something very strange. I'm going to resample, I'm going to treat the data, these x's that I've got in my hand, as the actual distribution. In other words, I'm going to treat it like it's a discrete distribution that has these samples. It's like a bag of marbles. And the marbles are the data that I've measured, and that's the distribution. It's not, there's not some continuous smooth function that describes the distribution. The distribution is that bag of marbles. I'm going to draw samples from that bag of marbles, but I'm going to pretend that when I draw the samples, I'm going to do it with replacement. So I'm going to, in other words, imagine I have not that bag of marbles, but an infinite number of copies of that bag of marbles all dumped into the same bin. So each data point that I observed occurs with equal probability, and I can draw each of them with equal probability. And what I'm going to do is I'm going to reach into that bin, and I'm going to draw in new samples from that bin. And those new samples will each one of them will be equal to one of the original data measurements. But some data measurements I'm going to pull out twice. Some of them I'm not going to pull out at all. Some of them I might pull out 10 times. Right? Each time I do this, I'm going to get a different mixture of the data. The values will all be the same values that I've already measured. So the reason that this becomes a procedure that people like is that you don't have to assume or invent anything. I don't have to do anything to interpolate between my data points some distribution or something that I believe describes this. Instead, I'm just going to take the data and assume that that's all I know. I'm going to resample from the data. This thing is called bootstrapping. It's called bootstrapping. The phrase bootstrapping comes from this, from a book, The Adventures of Baron von Munchausen. The Baron fell to the bottom of a deep lake. When it looked like all was lost, he thought to pick himself up by his own bootstraps, right? So it's like a nonsensical thing. You can't lift yourself up by your own shoelaces because, like if you work through the physics of that, like the forces, it doesn't actually make sense because you can't, you know what I mean? So how can you possibly estimate variability by resampling from the data you already have? Like the whole point of that simulation exercise I described was not to resample from the data, but it was to go back and resample from this distribution. But the point of this exercise is to say, well, you don't really know this distribution, you kind of made it up. You imagined it. And so what if you instead just resample from the data? Now the surprising thing is that if you have a reasonable amount of data, and under reasonable conditions, this works really well. And it's a topic of research still to fully understand the implications of bootstrapping and exactly when it works. But that doesn't stop people from using it. It is, at this point, really widely used. People do bootstrapping all the time. So how do you do it? It's really easy. That's the other reason they do it. Because all you need is a computer and some cycles, because it's expensive computationally. And as long as your code is correct, you just do it. Okay, so how does it work? You get your estimate. This is the estimate from the true data. Now I'm going to get a whole bunch of resampled estimates. These are going to be fake estimates that are just applying the same function, the same estimator, to not the original data set, but to samples redrawn from this data set, as I described before, with replacement. That is, I'm going to yank out, I think it says that on here. Right. This is a resampling method for computing the distribution of estimates, right? That I want a distribution of theta hat. I don't just want the theta hat that I've got from my data. I want to know what's the distribution of theta hats that I could have gotten if I had run the experiment again. Because I want to know how sure I am about the theta hat that I have. So the way you do it, just a second, the way you do it is by you draw a new sample out of the data that you have. A new sample will not be equal to the original collection of data because some things will be duplicated and some things will be missing. I go and I run the estimate on that new data set and I get a different theta hat. I do it again, get a different theta hat, do it again, do it 10,000 times. Now I have 10,000 theta hats, and one of them is the true theta hat, the one I estimate from the original correct data, and the rest of them are splattered around that, and I take that distribution and I use that as an estimate, an estimated distribution of the measurement errors and variability. Okay? And I can take a 95% confidence interval on that distribution. I can ask, trim out, where do I get to 5% on either side, or 2.5% on either side? That's the interval that I want. That interval is not necessarily symmetric, so this will handle asymmetric distributions or estimators that are going through funny nonlinear functions. So you might have your 95% confidence interval way off to the right and just a little bit off to the left, or way off to the left for humans, a little bit off to the right, compared to the true estimate, the actual theta hat from the data. And that's it. And the only real question is, how many of these things do I need to do? And the answer is, you won't find an answer to that in a book, or anywhere really. People run it. You have a computer. It's not that hard to run it a lot of times. So run it a lot of times until you have a pretty good picture of where the 95% confidence interval is, and stop it. Call it that. That's the answer to how many times you run it. It's all very loose, but it surprisingly works really well. Here's an example. This is a fun example from Efren and Tixirani. The best book on this topic was written by these guys. There's also a very short book on resampling methods that features Bootstrap by Good, I think is the last name. It's on the web page for the course if you want to read a brief thing about resampling methods. This is a much more serious statistical text. The first chapter, though, is a fantastic introduction, and this is taken from that chapter. Okay, so they just introduce the idea of the Bootstrap and show how to compute it and how it works, and give you a little motivation for why you might want to do this. And then they go on to do a more serious statistical analysis of what its properties are, which we're going to not talk about at all. Okay, so here's an example. New York Times, 1987. January 1987, heart attack risk found to be cut by taking aspirin. Okay, it's a pretty famous study. It's still believed that this is true, and many people that have heart issues take aspirin or half a tablet of aspirin every day. So what's the study based on? Let's see, I thought the data were in here. Here we go. So the summary statistics in the newspaper article are very simple. There's two groups, an aspirin group and a placebo group. This is the number of heart attacks observed in each of the groups. This is the total number of subjects in each group. So what we want to know is basically, how significant is this? Like 104 out of 11,000 versus 189 out of 11,000. Is that a really big effect, or is that something that could have happened just by chance if the aspirin wasn't actually doing anything? And so we want to get a sense of how significant, not only what is our estimate of the effect, which I'll tell you in a second how we're going to quantify, but we want to know how sure are we that that's not by chance, right? So we're going to do typical comparison to the null hypothesis, all right? So here's the thing we're trying to estimate. It's the ratio of the effectiveness, right? In the two cases, so it's 104 out of 11,000 divided by 189 divided by over 11,000. And that, if you just estimate that from these four numbers, you get 0.55. Okay, so it's like a 5% improvement. It's not a huge effect, but it's...
No, that's the ratio between the probabilities. The probabilities went down by half. Oh, calling it a 5% review.
Yeah,
It's a funny way to
yeah,
talk
you're
about
right. You're right. Fine. That's a better way to say it. Okay, so here, and actually you're right. They say that here. This is again taken from their introduction. If the study can be believed, the solid design makes it very believable. The aspirin takers only have 55% as many heart attacks as the placebo takers. Okay. Of course, we are not really interested in theta hat, this thing, the estimated ratio. What we want to know, of course, is the true thing. We don't know the true thing, because the true thing is like what would happen if you ran the study forever and you had an infinite amount of data. So what we have to do is get a sense of how sure we are about that theta hat. Like we need confidence intervals or something. Okay, so how are we going to do that? The next slide, I think, there, we just layered it in. So here's what they do. So you just take these numbers and assume that you're drawing samples out of these two bins, which have these probabilities, this many heart attacks per this many subjects, and then the second bin is this many heart attacks per this many subjects. Resample from the bins, compute this ratio, do that, I don't remember how many times, I didn't even write down how many times they compute this, but maybe we can guess. So this is a histogram. The bars have a height, which is the count, the number of times that thing was observed. And what you could see is that the highest bar is up around 1,200. So how many times did they run this? I don't know, probably 10,000 times, maybe more, 20,000 times. So they bootstrapped out of these data something like 20,000 times, and they got this distribution of values for theta hat. The true one is marked in red. That's the one off of the actual data, the one at this 0.55. And the rest of them, of course, are what you get out of bootstrap samples. And what you want to know is, like, what's the confidence interval? So if you take the 95% confidence interval, it goes from 0.43 up to 0.7. Okay? So you get some idea of roughly what the range is of where you think the true value is. Okay? All right.
Which doesn't include 1.
Which does not include, yes, thanks. Which does not include, which does not include 1. 1 would be, and sorry, I misread this earlier, but 1 would be no effect, right? Equal probability of heart attacks in the two cases. 0.55 means you're, as Mike said, down around half of the probability of getting heart attack. So this thing, with the confidence intervals, is 0.55, and even with the confidence intervals, even if you happen to have a study that by luck ended up on the good side of this, you're still pretty far away from 1. So this is a pretty strong effect. All right, question.
So are you drawing the same number of samples? Same number
yes. Typically, when you do bootstrapping, you draw the same number of samples as you had in the original data set. So when I was describing it over here, we're imagining that there are n samples here, n samples, and typically when you do this, because the point is that the variability depends on n. In almost all estimation procedures, it depends on how much data you have, right? We know that even in the most basic case of the sample average, right, that the variance goes down as sigma squared over n. So n matters. You can't just play around with that. You want to know how sure am I about this estimate, which was computed from n data points. So when you do your bootstrapping, you want to draw the same number, and they are doing that here. Yeah. Sorry, you had a question before, and
yeah, it's related to this. Is
there
kind of a general rule of thumb for the number of n samples that you should use?
So the general rule when you're doing an experiment is kind of work backwards. Ask yourself, how strong do I think? Get some guess about how strong you think your effect is going to be, and make sure you get enough samples to get an estimate that you can argue is statistically significant, right? This one is way statistically significant, right? If you're going to have an effect that's very subtle, then you're going to need a lot of data, right? Because generally, the precision of your estimate will get better the more samples you have. So that's one half of the answer to your question. The answer to how to do the bootstrapping is the answer I just gave to Shinima, right? That you need to, when you do bootstrapping, you want to resample the same number of data samples that you had in the original data, right? You're resampling from that data, but you want to collect the same number of samples, and it's with replacements. So you're not, it's like I said, you're going to end up drawing some of those things multiple times, and some of them not at all. Right? It's not the same values that you're going to pull out when you get n samples in the bootstrap. It's a resampling that is going to have some of those duplicated and some of those ignored. And each time you do it, you'll get different ones duplicated, different ones ignored, and that's why you get this variability, right? The estimate is bouncing all over the place here, and yet still it doesn't go beyond, you know, at least in terms of 95% confidence, it doesn't go beyond this range. Okay. So, like I said, once you have a piece of code together to do this, it's really straightforward, and asking a computer to resample things is usually pretty easy. Of course, the computer is running millions of operations to do this, as opposed to you just writing down something like this. So if you can do it in closed form, if you have a case, for example, where you're doing a sample average, you already know what the variance is of your estimate, and you don't have to go through this procedure. But if you're doing something more complicated, it's not an average, it's some complicated estimate, or you made up a new estimate. You have your own F that you stuck in here. Bootstrapping is a really good way to get a sense of how variable your estimates are. Okay? All right. By the way, I mean, when you start playing around with this, you do realize that it kind of breaks down if you have too small a data set. It starts getting kind of weird. Like, imagine if you only had 2 samples, 2 measurements. Like, what are the bootstrap samples going to look like? You're going to resample from that burn. There's only 2 values to sample from. So you're either going to get 2 of the first one, or you're going to get 2 of the second one, or you're going to get 1 of each. And that last thing you have, that's a 50% probability, right? Half the time you're going to get 1 of each, and a quarter of the time you're going to get 2 of the first one, and a quarter of the time you get 2 of the second one, and then you're going to average, so you're only going to get 4 different values for your estimate. You're not going to get this nice, thick, dense distribution. You're going to get 4 possible numbers, and 1 of those, and 2 of those are the same, because it's, right? So you're going to get 1 of those numbers twice as often as the other 2. So you're not going to get a very good picture of this distribution if you've only got 2 data points. Go ahead.
Yeah, so I guess that's kind of my question is, if you have some pilot data set with 3 animals in it, is there an appropriate statistical test to run? Or is there a kind of like general N where people look at, you know, like, oh, you have N of 5, you can bootstrap that and get some reasonable estimate? I know this is maybe a philosophical question.
Yeah, I'm probably not going to be able to give you a very comfortable answer in general. This is a squishy area to make decisions about bootstrapping and to decide, you know, how much data to collect in the first place is tricky. It really depends on the details of the circumstance. So I don't think I can give you a general statement. But the procedure is easy. Once you, like I said, once you have code to do this, it's very easy to run. So let's see, what is this? This is another one for strokes. If you do the same study I think the same study included an analysis of the number of people in these 2 collections that had strokes, not heart attacks. And these are the numbers. And now the value comes out at 1.21, and when you do the bootstrapping to get the confidence interval, 95% confidence interval, you get that the true theta is supposed to be between 0.93 and 1.59. So now we see that 1 is included in the interval, so we can't really conclude that this is very effective for preventing strokes. It's very effective for preventing heart attacks. No evidence that it's effective for preventing strokes. Okay? So in the same article, they go through that. All right. It's nice. I mean, the New York Times actually often does a pretty decent job of the data analysis. They occasionally make mistakes, but it's usually pretty good. Yeah?
Does it work the same for within subjects and between subject data?
That's a good question. How do I answer that? I mean, the general answer is that whatever, you just have to follow whatever the rules are of the thing you're trying to estimate. If this thing is partitioning data into between subjects versus within subjects, then you have to do your bootstrapping to respect that, right? You would have to keep them labeled by between subject and within subject. If this thing is not making use of that, then you don't, right? So I think the general rule is You have to keep track of whatever, like, so in this example, right, that we just went through, you had to keep track of the control group and the aspirate group, right? You had to resample from those separately. You couldn't throw that all into one bag. That would ruin the whole point of the study, right? So the point is that you would have to keep those labeled, and you have to draw from actually two urns, because the calculation that you're doing to get your estimate involves taking the numbers from the two urns and taking that ratio. Okay? So I would make the same statement about if you have some study that involves subjects and you're doing certain calculations within subjects and other things that looking across subjects, whatever it is that you're estimating between and within, you have to keep the data labeled in the appropriate way. So you will have to resample it according to those labels, conditioned on those labels. You can't mix across labels if you require those labels to do your estimation. I hope that, I'm trying to give you a very general answer. I hope that helps you at least to think about it. All right. Yeah?
I'm still a little bit confused about the logic of bootstrapping. So
yeah, it is confusing.
It seems that it's the reverse of the null hypothesis testing. So in that case, you assume the null hypothesis is correct, and you want to see what is the probability of getting the data.
Yeah, it's not a null hypothesis test.
Yeah, but in this case, you assume that your data, the probability behind it is exactly what is in your data, and you want to see whether the neutral outcome is possible in the simulation of this. So in null hypothesis, it's equivalent to assume the null hypothesis.
The null hypothesis, you do almost the opposite. It's like you simulate the null.
Yeah.
And you ask, is my true thing possibly in that distribution? Here you're doing the opposite. You're simulating something that's around my true thing, my estimate. This is the red thing is my estimate for my data. You're getting a distribution around that, and you're asking, does that include the 1, which is the null? Right? 1 is the null here.
Yeah.
1 would mean these things are, there's no difference between the placebo group and the aspirate group, right? They have the same probability. That would be if this ratio was 1. So you're asking, this is not a standard null hypothesis test. I guess I would argue this is a more sensible test, yes. Mike and I are not fans of null hypothesis tests.
But why is this logical?
Why is it logical? You don't think it's more logical? I think
You think it's more logical?
Yeah.
Okay.
Well, we haven't gotten the Bayesian.
That's true.
And if
You
you want
think we'll fix it
logical
then?
as in what's the probability the null hypothesis is true, that's coming up.
Yeah.
Yeah, this is
Fair
just a
enough.
confidence interval. It's not a proof that the null hypothesis is false. This confidence interval is no more giving you good demo of that with a rational probabilistic logic behind it than NHS.
Well, what you'd probably like for that would be to, I mean, they did something. I often wondered about this. Why are we writing this down as this ratio? Why do we not simulate the two urns and plot the two distributions? So let's imagine the placebo really is, well, you could. Maybe this is an interesting exercise to go through. We'll think about this. Why not plot resamplings from the two distributions and look at the overlap instead of doing this? That's what I'm thinking about. Why are we taking the ratio? Does it come out the same? I don't know the answer to that.
Those two distributions.
Yeah, no, I have two groups here.
Right.
I could resample from each of those, right? Why did they do it this way? Why bother with the ratio?
Because we're interested in how much improvement you get,
Right.
not in how often people get heart attacks.
Yeah, so the answer is a
and
little
by-
bit about how you want to state the result. You would like to state the result as some sort of like the chances, what are your chances of getting a heart attack relative to if you don't take the aspirin?
It's also worth backing up. Resampling from the individual distributions, the 104 out of 11 of 37 and the 189, those are binomials. We don't need to sample those. We have a closed form solution for what the distribution of a binomial is. We don't need this technology for that. On the other hand, the distribution of two binomial samples take their ratio. We don't have a closed form for, and so we use bootstrapping to approximate it as best we can.
So bootstrapping comes in handy where the thing that you're trying to model, you don't already know the math for. It seems complicated.
Or it's
And
difficult.
or it's
It would be difficult to work through.
Yeah.
But
In
doesn't
fact,
this,
often it would require just numerical calculations. You can't write it down.
doesn't this just give us a confidence interval for our estimated theta? Like we have no metric to know
That's
what
what it's
even our
giving. That is
true
what
theta.
it's giving you, right?
Like we
These green lines are the confidence interval around the red line. My theta hat from these data, this 0.55 is the red line, and here are the 95% confidence intervals around that, which are supposed to be interpreted as the true theta is 95% probability. The true theta is in this range.
But how do you know that? Like we have no metric here as to where the true theta is, since we're reusing our data, which can be like noisy.
How do we? You're right. In some sense, you're right, but in some sense, that's the whole endeavor, right? All of science rests on things like this. How do we know anything? Really? I'm sorry. I'm going philosophical again. I'm serious. I'm not making fun of you. I'm serious.
But in the logic that he's asking about,
Yeah.
you could say, a different logic would be, what are the hypotheses that wouldn't reject me for a confidence interval? What are the ratios which, if they were true, I would have been in their confidence interval, so I wouldn't have been rejected? You can't do that here, because the hypotheses are about a ratio. But the thing that we're resampling from are these distributions of data we collected. So you'd have, in order to be able to do that, you'd have to say, okay, if this were true, and I collected 11,000 samples of each, wait a minute, of each what? Because this is a ratio. This ratio would be true of 104 versus 189. This ratio would also be true of 208 versus 378. Because we're comparing a ratio independent of how often heart attacks occur.
Yeah.
So we don't have a way of using that logic inverted the way you'd like. Inverted as in, okay, what if the ratio were 0.07 or 0.08? Would that have rejected me? Because that hypothesis is a ratio. It's not what were the two individuals. So I can't bootstrap it. I can't compute it. It's messy. So again, the logic that will allow you to get to that rational conclusion of, I think my hypothesis is probably true, my hypothesis is that it's not one. That requires the Bayesian logic, which we're about to do.
Yeah, I mean, I think, for me, the bottom line is often that the magic of this is that it works for basically anything. Anything you want to write down, any function here. So this is a function where you gather these two sets of data, and you take the ratio of those two proportions, and that's what this function is. And if you had to go back and think through, well, how do I do a calculation to figure out what something like the standard error of the mean would be, like what that distribution looks like and what its width is, it would be really hard, if not impossible. And what you just use a computer, if you have a reasonable amount of data, and resample from it, and you get a pretty good answer. So this becomes a procedure that more and more you find people relying on, even though it's a little bit hard to say precisely and formally that it's correct. I told you, it's still a research topic in the statistics community. It doesn't stop people from using it. Okay.
Sorry. So if you set resample for two distribution,
Yes.
In that case, I guess you want them to overlap as little as possible if you want to see your hypothesis is true.
Yeah, that's right. You'd like to see that the placebo group and the aspirin group are very separated. Let's say you plot the percentage of heart attacks. So it's basically these two ratios, the one up in the numerator and the one in the denominator. And you plot those two numbers, and you plot a distribution of those two numbers. You have the value of those two numbers from your data. That's 104 divided by this 11,037 and this one. So you have those two numbers, and now you bootstrap each one of them separately. So you get a distribution for one, you get a distribution for the other, and you know, as Mike already said, you know what those are going to be binomial distributions, right? how do I choose out of this set? But you get those two distributions, and that would be another way to ask this question. And you ask, well, how overlapping are those two distributions? Is there any overlap? Or are they really, really distinct? Because that would indicate a clear effect of the aspirin. It's producing values that are very far from the values that you're getting out of that you would expect to get out of the placebo. I think people, the reason this is done as this ratio, I think, is mostly because in the end, you want to present people with one number. You want to tell them the thing that I get out of my study is this one number. What is this one number? The number is that your chances of having a heart attack if you take aspirin compared to your chances of having a heart attack if you don't. Like, how much better is it? How much lower is it? And the answer is it's 55%, right? So that's the number you want to give people. And then if you're going to give them that number, you want a confidence interval on that number. So that's why it's written this way, described this way, and that's why it showed up this way in the article. Okay. But you also see that in these kinds of analyses, there are always many ways to do them. There are many choices that you could have here. Many ways you could write this out. Many ways you could think about it. You could approximate things with Gaussians. You could work through all kinds of things. This is just what happened to be used in this study, and it's a very effective study. And another comment is just, and I often point this out to my students, when you're looking at data, if the effect you're looking at is really strong, it's not going to matter that much exactly how you decide to do your statistical test. It's just not going to matter. It wouldn't matter whether you did this, or you wrote down some approximate distribution and then you tried to calculate error bars from that, or you did what we were just talking about, bootstrap resampling from the two distributions and comparing them. All of those are going to lead to the same conclusion, which is this is a very strong effect. And it's not really going to matter. It's when you have a really weak effect that's kind of barely there, and that's when you worry in science. People start playing around and saying, well, which procedure can I use that'll get me something that's significant? Oh, if I do it this way, it's not quite significant. But oh, if I redo it this way, it comes out a little bit better. And then they start playing around. What's the phrase that gets used?
P-hacking.
P-hacking, right? So I hate that word, that phrase. So my view is, if you find yourself even tempted to do p-hacking, go back and do another experiment. Come up with another theory, come up with another kind of measurement. You're not working on something that's going to turn out to be that important if you're just barely significant. It's easy for me to say that. I don't work in the pharmaceutical industry, right, where I'm like trying to convince the FDA that my new billion-dollar drug is statistically significant compared to the placebo. And if the FDA decides it's not, then I'm not allowed to sell it. So it's a little different. There's a lot of incentive there to kind of push hard to make sure it comes out statistically significant. In my lab, if we don't have a strong effect, it's time to go back and build a better model or to measure a different kind of data. Okay, let's talk about Bayesian inference. We don't have much time. Jeez, this is bad. Oh, there's another question. You guys do not want, just saw that slide. Yes?
Oh, okay. I was trying to understand the relationship between the way you're doing the resampling and the shape of that histogram.
Yeah.
So it seems like if you pull like 80% of your data in each resampling, it's going to get thinner. Is that correct?
No, if you pull, if you don't collect n samples, you collect 0.8 times n, the distribution will get broader.
Broader if you pull a greater proportion of your original data.
The general rule is that the more data you have, the tighter your estimate distribution gets, right?
Right, so you can shift the confidence interval based on how much
No.
of the data
How many measurements you make.
Absolutely not true. I think you guys are
Talking about the size of the sample. What are you talking about?
Well, she's talking about the size of the bootstrap sample.
Oh, sorry.
Yes.
I thought
I
you
knew
meant-
that was happening.
I'm sorry. I misunderstood.
Okay.
You're talking about how many times I do this resampling
Not
process.
how many times, so the amount, so when you resample, that's a subset.
There are n data points,
Yes.
right? I made n measurements, capital N. When I draw one bootstrap sample, I do one bootstrap resampling, okay? I reach into the urn and I pull out n marbles. Each time I pull one out, I throw it back in, okay, and shake them. Pull out another one, shake them, put it back in, shake them. I'm going to collect n of them. So now I have a new fake data set, which has exactly n values, n measurements in it, just like the original data set. But it's not equal to the original data set because some of those marbles I pulled out a couple of times and some of them I never grabbed. Okay?
Okay.
That's one bootstrap resampling. From that, I get one estimate theta hat, one bootstrap estimate theta hat. It's different than the original, the true theta hat, the one that I got from the original data, because this one came from this fake resampled data. That's one sample. I do that 10,000 times. Each time I get n numbers out, I get a new theta hat, and I collect up all those theta hats. I have 10,000 of them. So it's what's complicated about this procedure is very simple, but it's kind of nested, right? I have to do this resampling, I have to get n of them, I have to do that, estimate my theta hat from those, and then I have to do that 10,000 times, and then once I got all of those, I make a histogram of all of those, and I look for that's what that distribution was. It was a histogram of those. Okay? But each one of those estimates came from a resampling of the n data points. Okay? All right. The 10,000 is the number that I'm kind of making up. You can make it 1 million. You may have to gather as many as you need to get a decent looking distribution is kind of the, and you can't err by gathering too many, so if compute time is cheap, gather 1 million. Gather 10 million. It's cheap. Let the computer run. Is that right? It's not going to get worse. It'll converge, and then it won't get any better at some point. It won't be worth it to gather 50 million. 10 million is plenty. Probably 1 million is plenty. Probably 10,000 is plenty. But if you only gather 10, you're going to have 10 examples. It's not going to be able to let you see what the distribution looks like. So you're going to need more than that, right? Okay. All right. We talked about maximum likelihood estimation. We talked about the fact that it is a pretty weird construction because we're taking a probability distribution, which is conditional, and is usually read as a function over x conditioned on theta, where theta is some fixed value, and we're doing it backwards. We're letting x be fixed. X is supposed to be the random variable. We're fixing it, and then we're asking what is theta. That's a weird thing to do. And a much more natural thing to do, but it will come at a cost. And this is the core of the debate between the frequentists and the Bayesians. A more natural thing to do is to say, actually, this is what I wanted. I didn't want this probability of data given theta. That's the likelihood function, if I think of it as a function of theta. I wanted this. I want a distribution over the thetas that could have led to the data. I want to compute it this way. I want theta to be a random variable. I want to know what's the probability of the true theta having various values, given that I've observed the data. The data are fixed. I've got them right here. They're sitting in front of me. Here are my n data points. Now what? What is the distribution over theta? That's what I would really like. And the way to go between this thing and the flipped version of it, this is p of theta given data, rhymes, and this is p of data given theta, right? These are the same, except they're backwards, right? The data and the theta have been swapped, so how do I go from one to the other? That's Bayes' rule. Right? It's just, which is like the definition of conditional probability, and you've already seen this, and probably you saw it before you took this course, right? So the way we write this out is that the joint distribution is the probability of the conditional times the thing you're conditioning on. So this p of data given theta times p of theta, that's the joint distribution, p of data comma theta. And the same thing would be true over here, p of theta given data times p of data. If I were to pull this on the other side, that's the joint distribution. So those two things are equal. And if I divide out the p of data, then I get this expression. Okay. So what does this tell us? If we want this, which is the thing maybe that would make more sense to optimize or to look at, I have to take the likelihood and I have to do something to it. I have to multiply it by this, p of theta. What is p of theta? This kind of made sense. This is a description of how my measurements arise. This is how it's like the measurement distribution. If you like, it's the noise in my measurements. This is how my data are related to theta, including their stochasticity, the fact that they're variable every time I make a measurement, I get a different value. This is something about what I know about theta before I make any measurements. So before I even do the experiment, I probably have some idea of what theta is. Maybe there are hard constraints. Theta has to be positive. It a positive valued number of the thing that I'm looking for. Maybe I know that it lives in some range. Maybe I already know because other people have looked at and measured this thing that I know roughly where it is. And it's around 0, and it's kind of, I don't know, it's probably not too far from 0. It's within plus or minus 10 of 0. So maybe I have some prior knowledge. So we call this the prior probability distribution on the thing we're trying to estimate. This is what we know before we make any measurements. After we make measurements, we've got this, the likelihood. We multiply the likelihood and the prior. And when you multiply the likelihood and the prior, you have to normalize them. And the way you normalize them, or what you'd like to do is to take a slice through it. That is, you want to conditionalize on the data. And the way you do that is you have to normalize the joint distribution that's in the numerator, and that's what this is. Another way of saying that is P of data is just the joint distribution, P of data, comma, theta, integrated out over theta. So it's like you take the numerator, the product of these two things, and you integrate out the theta. That's what P of data is. Notice that if you're thinking about this in terms of theta, there is no theta in the denominator. This is just a scale factor. So the theta is only up here, here, and here. And if you're thinking about it in terms of estimation, thinking about how do I figure out what's the best theta given this thing, the best, you might decide that the best, the one that I'm going to choose, is the one with the highest probability. So I'm looking for the maximum of this thing over theta. And if you're going to maximize this over theta, well, the thing on the right, you're really just maximizing the numerator. The denominators doesn't depend on theta, so it's not going to matter. It's just rescaling the whole thing according to the data, but it's not affected by theta. So the thing you're going to do is just maximize the numerator of this if you want to compute this as a way of getting an estimate. Okay. So the thing, this is called a prior, this is the likelihood, we already knew that, and this thing is called a posterior. But the thing that we really added here to the mix, we flipped this around. We made this more sensible. This now is written the way it kind of should be. But there was a cost, and the cost is that we now have to figure out what to do, what to put in here. We have to make a decision about what to put in for our knowledge about theta before we did the experiment, before we make any measurements. We need a prior. So that's the crux of the argument is about, the frequentist would say, you have no right asserting a prior on theta. You shouldn't be doing that. You should just work off of this. This is the only thing you really can be talking about. This is your model or your description of where your data came from, and that's all you should be thinking about. You shouldn't be making stuff up. And the Bayesians would say, well, yeah, you're fooling yourself because this doesn't make any sense. And really, you always have some concept of what theta is before you do your experiment, and there are often constraints on it, and why not put those into the problem? Why not build them in? So, and the argument goes back and forth, and it still goes on today. And the truth is that in modern times, you can do things to stick something in here and leave this sort of parametric and use it as a sort of a knob for controlling how your estimator behaves as a function of how much data you have. So it turns out there's tricky ways to sort of do this kind of estimation and use this to your advantage in the context of even using bootstrapping to determine what the knob should be in order to minimize the variance of your estimates, right? So there's all kinds of things you can do in modern computer-oriented data analysis that allow you to do this kind of estimation and do something sensible over here. And we'll see some simple examples of that. All right, so let's just, we're out of time, but let me just quickly show you what this looks like. So if you're doing the coin flipping case, right, you can imagine, like beforehand, you know something about the coins you're going to be flipping. Like maybe you assume you have no idea what the probability of heads is. Like it can be, the coin can be anything between extremely biased toward tails to extremely biased toward heads, all with equal probability. That's probably not true for most coins. You might think that most coins look more like this, like most of them are kind of around 0.5. It's probably a lot tighter than this. If you take coins out of the mint, normally produced coins, they're probably very, very close to unbiased. And so you couldn't use a tight little distribution for the prior. Or you might think that, well, this is coming from that mint over there that tends to mint biased coins because they do two kinds of metals and one side is heavier than the other. And so they almost always are biased toward heads. So I'm going to assume that the distribution looks like this. So you put in a prior distribution, and then you go ahead and you start flipping the coin. That's going to be your likelihood. Right? So these are your priors, 1, 2, 3 examples of priors. And how does this work? Well, you multiply your prior by your likelihood. And we already talked about what the likelihood looks like for the coin flipping case. It's a ramp. If you flip a head, then it's a ramp this way. If you flip a tail, it's a ramp going the other way. You probably remember that because we went through it, right? So you get these combinations of ramps, positive and negative ramps, and you multiply them all together to get the likelihood. If you've only got one measurement, you take your prior and you multiply it by your likelihood. This case is the one for heads, and you get this, which is the posterior. And these things, 1, 2, 3 posteriors here for these 3 priors, they look kind of like, you notice that this one turns into, well, it gets shoved over a little bit, but just a little bit. This one gets shoved over a little more than it was originally. And this one changes pretty dramatically, right? Because this one had no idea what the right answer was, and now it turns into this. Okay, so the prior is going to get shaped or modified by the likelihood. And the more coins we toss, here's what happens if it's tails, it goes the other way. And if you toss, let's see, did that? If you toss a lot of coins, so here's, after you toss 75 heads and 25 tails, so what I'm going to do is I'm going to take each of those priors and multiply it 25 times by the heads prior, that's this ramp, and 75 times by the heads prior, and 25 times by the tails prior, that's this one, and kind of the heads one is stronger, so you're getting pulled more to the right. And sure enough, what started out as that nice smooth prior with a walk-up that was centered at 0.5 gets moved over quite a lot. And the one that started out, how did this one start out? Biased to the right, also moved to the right. In fact, you notice that after 100 coin flips, these 3 things look almost indistinguishable. So what happens is that you've got this product of terms, because each of the samples comes with a new term in the likelihood, right? A product of another probability, because they're independent draws. So you multiply the prior, that's what you start with. You make one measurement, you multiply the likelihood of that measurement. You make another measurement, multiply the likelihood of that measurement. Make another measurement, multiply the likelihood, and each time you make this multiplication, you're chaining together all these things. And you can do it incrementally. You can hold on to your current posterior, and you make another data measurement, you just tack it on, multiply. Make another data measurement, keep doing this, right? So you incrementally update this thing one by one as the data come in. And after you've got a lot of data, the data dominate. They sort of take over. The prior doesn't have much effect after you've got a lot of data. When you have only a little bit of data, the prior has a very big effect. You saw that after one coin flip. The prior had a huge effect. And the prior eventually goes away. So the prior becomes something that has an effect that depends on how much data you have. And when you don't have much data, you have to rely on the prior. When you have a lot of data, then the prior basically steps out of the way and says, just go with the data. And that's what you see here. These basically are effectively the same, even though they started out with these 3 different priors. Okay, we're out of time, but just to close that out, you can put confidence intervals on this. These are called Bayesian confidence intervals. It looks just like what you did with confidence intervals we talked about before, but now you're going to do it on the posterior. So here's the posterior, 2 heads and 1 tail. This is the posterior. Here's your 95% confidence interval, and it gives you these 2 numbers. You just read them off of the cumulative. Right? So here's your confidence interval. You get a different confidence interval on this one, and you get a different confidence interval in this one. Right? So you can measure off confidence intervals the same way we have been doing all along, except now you're going to do it off of the posterior, not on the likelihood, on the posterior. So these are going to actually represent probabilities, regions of probability over which the true theta lives. And so it's now, everything is now much more consistent and sensible because we're talking about things that are probability distributions. Okay, that's it. We'll continue next time.